Hello, everybody. I'm Denis. I work at Microsoft on Cosmos DB. I do chaos engineering and consistency testing there. But today I want to talk about something else. Today I want to talk about something else. Something a little bit more applicable to a larger audience. During my career, I ran into the task of implementing transactions spanning different data sources several times. So today I'll overview the latest research in this area. But before we continue, we should ask ourselves, do we really need the transactions? Maybe we can let the system work without the transactions and deal with consequences. Well, it's a valid question, but things may get funny. Sometimes anomalies may be exploited by hackers to gain some profit, and in this case, the errors they are not random. There is a malicious stuff happening, and we may run into serious problems. I try to find some post-mortem analysis where the lack of the transactions lead to similar disaster, and I found this gem. Basically, the hackers, they put some bitcoins on a stock exchange, and then they initiate multiple withdrawal operations at the same time, and some of them succeeded. But the operation was going to withdraw all of the money, but it succeeded several times. So the hacker was taking money from the Bitcoin common account, and it's managed to withdraw 12% of all money. And it's not the only case. In this case, the Bitcoin exchange tolerated the fail and continue operation, but another Bitcoin exchange, it closed after the similar error. So let's take a look at what people in the industry think about the distributed transactions. This is a very popular article by Pat Helland, and he exploring how to build infinite scalable services without transactions. But why he wants to avoid transactions? He wrote that when developers start using distributed transactions, the project founder because the cost and fragility make them impractical. But this paper was published 15 years ago, and since then there was a lot of research activities in the domain of the distributed transactions. And there is a multiple protocol appears. So maybe what used to be true in the past, what used to be a common knowledge, isn't true anymore. So in this talk, we're gonna explore what did fragility mean in the 2000s. Are distributed transactions still fragile now? And what's the cost of using distributed transactions? In the 2000s, I wasn't a software engineer. I probably was at school or I was at school. And I don't know what people used to do the distributed transactions. So I did some research. I went to Stack Overflow and tried to find the earliest questions about transactions. And I found that the best way to distribute transactions over more than one database is don't do this. And there is a reference to XA. What is a XA? XA is a specification for one variant of distributed transactions. And I went and found a vendor who implements this XA protocol, and I took a look on the documentation. And I found that if a transaction coordinator becomes unavailable, then transaction and the associated data cannot be changed until the transaction outcome is resolved by external intervention. What is external intervention? Is an on-call person who gets paged during the night, start finding the laptop, connect to production and start investigating what is going wrong. And probably it will take 20 minutes. So the system will be unavailable for 20 minutes. And it indeed looks very fragile. The domain of the distributed system is full of impossibility theorems. One of the impossibility theorem is a cup theorem, that we should choose 2 letters out of 3, where the letter stands for different property. C stands for linearizability, A stands for availability, and P stands for partition tolerance. Maybe the same is true for the distributed transactions. Maybe we just doomed to choose between availability and strict serializability. Well, there is indeed a similar theorem, but it way more permissive and has a way more nice acronym. It's Snow theorem, and it's about read-only transactions. It doesn't say that the system can't have write transactions, but it just focuses on the read part. And just like with the cap theorem, we free to choose 3 letters out of 4. So let's see what they stands for. C stands for strict serializability. Basically, all of the transactions, they are being executed in order, in some order, and this order respects the wall clock. N stands for non-blocking. So if I, as a client, connected to some node of the system where there is a data and I want to get them, the node can respond to me immediately without contacting any other nodes in the system. Or means that when I read a key, I received 1 value from the node, and I need to read only, and I need to do only 1 read per key. And V means that the read transactions, they don't block write transaction, and write transaction don't block read transaction. And the closest thing to availability here is non-blocking stuff. So we can't throw away non-blocking. So if we keep N and then keep S and keep V, then it means that we can do strict serializability using a couple of round trips with the storage. And it's much better than the initial hypothesis that we need to choose between availability and the strict serializability. And it's better than the 20 minutes that I was talking in the beginning. So we figure out what fragility meant in 2000s. So we figure out if it's possible to do distributed transaction now to be... We figure out if it's possible to do available distributed transaction now, and now we gonna find out what is the cost of using distributed transactions. So how I'm going to calculate the cost? Writing a distributed transaction isn't an easy task. There is a lot of factors and properties that we should do right in order to get a viable product. And if any of the property is violated, the whole endeavor is doomed. And this actually put us in the domain of Anna Karenina principles. Yeah, happy families are all alike. Every unhappy family is unhappy in its own way. If the system has a lot of properties and we have restriction on these properties, then implementation of this system, they all similar because we basically physically can't do the other way around. So I'm going to pick one database and estimate the cost using this database, and then extrapolate to the other ones. Of course, I choose Cosmos DB. I know this database more than all of the other, and it's a really good database. And it has a distributed layer somewhere on the bottom, and it provides multiple APIs. There is a native API, MongoDB API, Gremlin API, Cassandra API, and also there is a etcd API. You can run Kubernetes using Cosmos DB instead of the etcd to get better availability. And it supports multimast, CRDT, a lot of stuff. But the only thing that I'm going to use here is a conditional update, compare and set. So if you're using any database which contains compare and set, it's possible to do distributed transactions across of these instances of this database, or different instances of databases. Actually, I lied. I'm going to use another property of the Cosmos DB. When you start using the Cosmos DB, you buy throughput. And you can buy, for example, 1,000 request units per second. And each operation in the Cosmos DB, the cost of each operation in the Cosmos DB is expressed by request unit. And this is provided in every response that the database gave back. So I'm going to run, to implement different protocols of distributed transactions, run them on the same workload on Cosmos DB, calculate the request unit, and estimate the cost using this way. Why the cost matters? First of all, I told that we need to provision some throughput, and if the cost is low, then the less money we're going to spend. Also, this request unit, it's a good estimation of work that's being done. So we can use this as a measure of work. The more work we do, the higher the latency. You may ask why I don't measure latency. Because it's hard, and measure the cost is much easier. I can get the reproducible results on public transport Wi-Fi, and the results will be almost the same as running on a high-speed internet connection. But with latency, I need to control all of the environment, and it's much harder thing to do. So we figure out how we're going to measure the cost, why the cost matter, and now let's talk about the workload. So I picked this workload. It's a mixed workload with 80% of reads and 20% of writes. There is a multiple threads, and there is a write transaction. It's basically a regular bank account example. The write transactions transfer money between different accounts. The read transactions read balance from free accounts. There is a fixed rate of collision between the keys, between the accounts on the ongoing transactions. And I retry all of this workload in a loop until a fixed number of transactions are successfully executed. So basically, in each workload, I do the same amount of work. For example, execute 10,000 transactions. Then I normalize the costs of this workload by the number of successfully executed transactions. Remember I told that there is a lot of protocols in the recent years. Actually, it's underestimated. There is way more protocols, and there is a lot of them. I can't cover all of them during this talk, and we need to use some selection criteria to pick the interesting one. And I use the following selection criteria. So first of all, I'm focusing on the familiarity of the model. So I pick ACID because it's a very familiar model if you use with the relational databases. And I want you to use your intuitions that you already have for the relational databases when we work with the distributed databases. The second part is we must use this transaction with the existing storages, because a lot of people write application, and it's a very little amount of the people who wrote storages. And if you're working on the application and you want it to use transactions to avoid such problems that we discussed in the beginning, it's unfair to force you to write your own storage. So it should be client-side transactions. And by the same reason, we don't want to use some specific hardware. So we want the general solution. So using this selection criteria, I picked the following transactions protocol. First of all, it's a Twophase commit, Paxos commit, Eiger, Granola, Percolator, and Ramp. So let's start with the Twophase commit. It has some known flows. Basically, it's the protocol that was the protocol that XA specification uses. So we already know that there is some issue. But it's a foundation for all of the other protocols. So it's good to understand how it works. So we have a client who wants to execute the transaction. We have a coordinator. We have two storages which store some data. So the client, it sent a transaction to a coordinator. Then coordinator executes the prepare phase of the transactions. So it sent messages to the storages receive the messages, then they lock the records and respond the current value to the coordinator. When I said that the records are locked, it's not something that holds in memory. It's a materialized lock. So nobody can access this data. We even may remove this data from the database, and everything gonna work. And so coordinator received this data, then it evaluates the transactions using this data that it received. So it came up to the decisions that A should be 50 and B should be 150. And then it executes the commit phase. Basically, it asks the system, please unlock the records with the new value. So we unlock the records, and after this point of time, the transaction is executed. We get the confirmation from the storages, and then we send the confirmation to the client, and the transaction is done. Two-phase commit, it's about commit. It's not about the transactions. So there is might be different variation of the two-phase commit, but it's one of the possibilities. Let's estimate the cost. So I run the workload on the Cosmos DB and got the following data. Baseline is executing of the workflow without any transactions protocol and without the conflicts. So this is a baseline, and we can't get any better results than that. Two-phase commit cost 13 request units, so it's 55 increased over the baseline. Pretty good results. But two-phase commit has problems. One of these problems is happened when a coordinator goes down during the mid-time of execution of the transaction. So it's unlocked one value, but failed to unlock another. And since the only storage about the future value was lost, we don't know what is the current value, and we don't know, and we need some manual intervention to guess, basically to guess and hope that we are right. This is one problem of the two-phase commit. Another problem of the two-phase commit is throughput issue. All of the data that, all of the transactions that we're executing in the system, they go through one coordinator. So after there is a lot of errors coming to and from coordinator, and each error, it's a message. So, sooner or later, we exhaust all of the throughput, we reach the saturation point, and everything became slow and and unusable. So we have two problems with two-phase commit, availability and scalability. Surprisingly, both of these problems can be fixed with the same solution. So I'll focus on the availability problem, and then we solve the scalability along the way. We know that if the coordinator loses its state, the database will be locked and require DBA intervention. What if there exists a protocol, fault-tolerant, replicated state machine, which can fix this problem? Of course, this protocol exists. It's Paxos that we heard from Hydra on the previous day. And we can just take this replicated state machine and run coordinator on top of Paxos. And it will solve the availability problem, and it also allow multiple coordinator coexist and distribute the load. This idea is called Paxos commit. It was proposed by Jim Gray and Lester Lampert in 2004. Actually, they use not Paxos and not a replicated state machine, but a CNOT protocol. It's the simplest form of Paxos. So basically, we can think of multi-Paxos as a replicated append-only lock. And CNOT protocol, it's a write once register. It's the simplest thing. It's very easy to implement, but I'll put this out of scope of this presentation. And for for simplicity, we just will store the state of the coordinate inside of the database itself. Any database which is distributed and provides strong consistency has the paxos somewhere underneath it. So basically, it's true. We still call this as a paxos commit. So let's discuss how it works. So again, it's a client coordinator and databases which store data and which store state of a coordinator. So we send a transaction to a coordinator. Then the coordinator creates an object representing the state of the transaction in the database. Once the object is created, it initiates the prepare phase. The prepare phase, just like in the two-phase commit, logs the data, but unlike two-phase commit, it stores the previous, the current value in the database itself, and also a reference to this object representing transactions. So then it returns the current value to the coordinator. Coordinator evaluates the transaction, then it updates the object representing the transactions, and once it gets a confirmation, after this point of time, it's free to say to the client that transaction is committed. And then in the background, it's proceed further to unlock the locked records. After it gets confirmation from the nodes, it deletes the object representing the transactions, and the execution of this transaction is done. Let's see the results. So two-phase commit was 55 increase above the baseline. Paxos commit gives us 88% above the baseline. It's pretty good result. Now we can go further. We can see on this diagram that all of the state of the coordinator lives inside of the database. So we can, because of this, the system, if a coordinator goes down, we can immediately run another coordinator. We can even run another coordinator in parallel, and they will compete one with each other for several times. Or we can ask the client to act as a coordinator. Basically, it's the same diagram, but all of the actions which coordinator used to do now is the responsibility of the client. This approach solves the other problem, the scalability one, because we distribute the role of coordinator to different clients. But it has problems. It's a conflict. What if two different clients want to update the same record in the database? So we have client one who wants to update the database. It's creating the object, then it's logged the record. And we have another client who also wants to update the record A. It creates the object and then goes and tries to log the corresponding record. But it gets a conflict. What then this client can do? It can go and try to abort the first transactions by setting its status to aborted if it's still in pending. And once it's aborted, it's free to continue its execution. At some point of time, the first transaction will notice that it's aborted when it fails to change the status from pending to committed, and was forced to retry. The downside of this solution that there is a lot of retries. So we are doing some work and then we're retrying this work. So we have, so the cost of the execution grows up. I get curious how fast they grows up. So I start playing with the conflict rate and got the hockey stick. On the y-axis, there is a cost multiplier compared to the case when there is no conflicts, and on the x there is a rate. There is a conflict rate. It looks bad, but actually it's not so bad, because with two-phase commit we have two problems, availability and scalability. With Paxos commit, we solve the availability problem, and then we have a choice, either to have a scalability issue if we reach saturation point. But not all the system reaches saturation point, so it might be okay. Or we can choose to have high cost on the conflicts. But again, not all transactional system operate when there is a lot of transactions trying to update the same records. So again, it's also might be fine. Since we introduce a new scenario when we have a coordinator, when the client's works as a coordinator, let's take a look on the costs. So it's not great, but also not terrible. We see that. We see that the cost of coordinate of the case when clients work as a coordinator goes up even when there is no conflicts. Why it happens? It happens because when we have a single coordinator and there is a read-only transactions goes in, we can reorder read transactions to execute when there is no updates happening to this key, and then we can do reads in one round trip. But when there is a multiple request, there is no such luxury, and we need to run read transaction just like we do the write transaction with creating the object representing the transactions, locking the records, reading, unlocking them, deleting the object representing the transaction. And there is a lot of read transactions in the workload. It's 80%. So it's not surprisingly that the price goes up. And I don't even speak about the third column. It's terrible. Let's see how we can improve this. So we will focus on, since the problem is with read-only transactions, let's focus on them. There is a such trick which called double reads. Imagine that we have a single database and some client who tries to read the value. So we start executing the read process at moment T1, and it ends at moment T2, and we read some data. We can know that somewhere in the moment between T1 and T2, there was a moment when the state of the database was equal to the read value. Now, if we do the second read, and it returns the same value. I mean, it actually returns not the same value, but the same version to avoid the ABA problem. That we know that in the moment since T2 to T3, the state of the database was constant. And basically, we executed that transactional read. Yeah, now we can do the same trick with multiple databases. And when do with multiple databases, it's the same. We found interval when the state of both database was stable. If we got some new result, we just keep retrying until we get the same result. And in this case, we executed the transactional read. Let's take a look on the price, how it was improved. It was improved pretty good. It was 800 before, and now it's almost 100. And even the case when there is a 100% of conflicts drops significantly. So we improved with double reads, but we can do even better. There is a paper about the Eiger transactions, and it's at the Lampard clock. So basically, when we execute, when we do any operations on top of the database, we have some counter, and we can amend this counter. When we do Twophase commit over several instances of the nodes, we execute the prepare phase, we got the current time, we pick the maximum, we increment this, and during the commit phase, we distribute this new maximum time to all of the nodes. So this allows, and we store when we update a record, we store the time when this record was updated. And also we store the current time of the server. So when we do read, and these conditions is true, basically we read several keys, we pick the maximum of the modification time, and if this maximum of modification time is less than the minimum of the time on each node, then we know that this read was transactional, and we can serve the data to the client. If it's not true, then we have several options. In the paper, they had the multi-version concurrency control, and they did the follow-up read up to 2 reads, so 3 in total to resolve the transactional read. But in this case, I just fall back to double read. And this is the result. So we make them lower by 10%. So far, we were focusing on the read transactions. Now let's focus on the write transactions and try to make them faster. There is a Granola paper which focusing exactly on that. So this Granola paper, it picks the subset of write transactions called independent transactions, and then execute this really fast. Let's take a look how it works. So we have a client with a transaction that we want to execute. We have 2 storages, A and B, and in each storage we have time, which is not per record but shared across, which is just time on this server, and we have the current value. So we want to execute the transaction. We send the transaction to one of the storage. Then we assign the time to this transaction and bump the time of the server and store the transaction inside of the database. When it's done, we send a transaction to the rest nodes participating in the transaction. We assign time and save in the database. After that point of time, the nodes start gossiping the time that they have assigned to the transactions. And once each node collected the gossip from all of the nodes, it picks the maximum timestamp and execute and postpones the execution of the transactions until all of the transactions with lower timestamps are executed. So in this case, it's only 2 databases. So just after we send the transaction to the second node, it can immediately pick the maximum between local time and the remote time and put transaction on the queue. Then it responds to the second node. The second node gets the time of the first node gets the time of the second node, picks the maximum, and this maximum, again, it will be the same as on the second node, and we postpone the execution of this transaction until all of the transactions with the lower timestamp are executed. Immediately after the first transaction received this response and figure out that every other node saved the transaction into the storage, it answers to the client that the transaction is executed. Then in the background, at some point of time, these transactions are actually being executed on each node. In the first node, it also bumps the time because the assigned time is much higher than the time of this local node. After this, the nodes start gossiping again that the transaction was executed, and once they know that the transaction was executed on every node, they delete the object, the transactional object, and just keep the updated record. So let's take a look on the cost. Oh no, not on the cost. What the independent transactions are, because this Granola paper, it's not about all of the transactions. It's just about some subset of the transaction. So basically, when we don't have when different nodes came to the same decision, either to commit or abort a transaction, then this transaction is independent. So if we don't have any conditions on the records that we are updating, then it's fine, it's independent. So one of the examples, we just can set accounts to some amount of money, and it's going to be all right. We can do the transfer of money between the accounts, and it's also going to be all right. Or we can even have conditions on the transactions, but in this case, in this case we have a condition of the blacklist. So we check if a transaction in a blacklist, if a record in the blacklist, then we abort it. Otherwise, we proceed. But we want all of the nodes in the system came to the same decision about whether to proceed or not. So in this case, this blacklist must be replicated on all nodes in the system. And in this case, we can came to the same decision. And the nice part that in case of blacklist, modification of the blacklist will be also independent transactions. So everything works fine. Let's take a look on the cost. So it's really good, isn't it? Because the transactions, even if they have conflicting keys, they don't conflict, they getting reordered, and they wait in a turn to be executed. And everything works fast. Okay, so what have we done? We covered the read transactions. We see that there is a subset of the transactions that can be executed fast, these independent transactions. Let's try to cover the other types of transactions, because not all of the transactions that we want to execute are independent. So in the relational databases, this was already solved. So people have this trade-off, either to be correct or to be fast. And and they came up to this idea that when the violation of the consistency is expectable, then it's not a violation at all, and they renamed this and called them isolation levels. So we have a strict serializability when there is no any anomalies. We have serializability when we have stale reads, and we have the other different types of isolation consistency. And in each isolation consistency, we allow some anomalies to happen, but we get some performance gain out of it. So let's. So far we were focusing on strict serializability and serializability. So now let's step down and take a look on the snapshot isolation and the right screw. What the right screw is? We imagine, again, we're talking about the bank accounts. And there's several accounts, and you and your partner, you have access to both of these accounts, and at the end of the month you need to pay some rent, but also you want to buy some treats for yourself, and you go to the ATM and you want to withdraw some money. So you see the list of the accounts, and you decide, okay, if the other account has some money, I will withdraw with the other account. And your partner decides exactly the same thoughts, but he chooses the other accounts. And they execute this. On the serializable execution, one of these transactions should fail, but on the snapshot isolation, this transaction will succeed, and this results in the right screw anomaly. So we allow some anomaly to happen on the snapshot isolation, but what we're gaining by this? What the performance benefits? And on the snapshot isolation, one of the stuff that we can get is we can execute a transaction unless some global condition has changed. And one of the examples of this global condition can be, for example, please do a transaction X if I'm still a leader. So these kinds of operations are really common in the distributed systems when we need to get log on some resource, and when we get a lock in the distributed system, we get a fencing token, and when we execute an operation, we should check that the fencing token hasn't changed. So this is one of very useful stuff. Another useful stuff is we want to execute an operation until some cache value is invalidated. So in our example, let's take a look on the bank account examples that we discussed before to see the last example. So previous workloads that we used, we were transferring the money between two accounts, and we were reading from 3 accounts. Now we introduced some fraud detection system in our bank, and we want to stop executing, and we don't want to even to start executing a transaction if the account's in a blacklist. So each initiator of the transaction caches a blacklist, and when it's before executing a transaction, it checks if the accounts are in the blacklist or not. Once it's decided then in the blacklist, it just rejects the transaction before it's even started. Otherwise, it starts executing of it. But we want to avoid divergence between the cached blacklist and the actual blacklist to prevent fraud as fast as possible. So the solution is to include a condition on the blacklist version into all of the transactions. And these kinds of transactions can be really fast with under snapshot isolation. So I implemented this and ran on the current transaction protocol that we covered. And yeah, everything is better for Paxos commit with double reads, and for Eiger. But Twophase commit and Granola working is fine. But for Granola, I was measuring, remember, I was measuring only the cost, but not the latency. And since we, in Granola, postponed the executing of all of the transactions until the previous transactions are executed, and in this case, we have a condition of the on the same record across all of the transactions that we're executing, basically we execute all of the transactions in sequence. So we have a high latency, and these results is basically the same as having assigned coordinator. So we should compare Granola's data not with the Paxos commit and double reads, but with the Paxos commit with coordinator. So it works a little bit slower. But what works great in this scenario is Percolator transactions. Percolator transactions, they realize snapshot isolation, and they shine here. So we want to execute so what we have here, we have an additional entity. It's timestamp server. It's before executing the transactions, we need to contact it and get some timestamp. And it's possible to implement the timestamp server to be fault tolerant without flushes to any disk. And but it's out of scope of this presentation, but it's possible to do this. Let's see how Percolator works. We want to execute these transactions. First of all, we go to the timestamp server and get the timestamp. Once we get the timestamp, we go to all of the data nodes, and we read data which is the latest but not greater than the timestamps that we provided. So once we get all of the data, we can evaluate the transactions, and we see that the blacklist version is the same that we expect. So everything fine, and we execute the transactions. Once we prepare this write set, we send it to a coordinator, and once the coordinator got it, basically execute a slightly modified two-phase commit. So what it does, it goes to the data nodes and prepare and execute the prepare phase. But this prepare phase, it checks if the latest version, if the timestamp of the stored data is less than this provided timestamps that we got on the first state of the first step. If it's true, then we log the table, we log the record. Otherwise, the prepare fails and we need to retry the transactions. So let it be a success. So we get the data, then we go to the timestamp server, we get the new timestamp. This new timestamp is a timestamp of the commit. So this will be the final version of the records. Then we mark the object representing the transaction as committed, just like with Paxos commit. Then we return to the customer that the data is committed, and then we execute the in the background. We unlock the records, delete the object, and the execution of the transaction is done. So the price for the Percolator, it's pretty good. It's 80%. It's better than Granola. It's better than Twophase commit. It works. And now we're going to the last one, to the atomic isolation level. It's a orthodox isolation level. It's slightly, it's not the part of the ACID specification, but it's somewhere in between snapshot isolation and read committed. It doesn't have the read screw, but it introduces a new anomaly called lost update. Let's see what the lost update is. So we have 3 accounts, and we have 2 transactions that executes. And in these 2 transactions, we transfer money from account A to account B, and then from account B to account C. Under the serializable model, we expect that the amount of money in the system remains the same. So it was 300 in the beginning of transaction, so it must be 300 in the end. But here it's only 200 in the end. So we run in the anomaly called lost update. It looks like a madness that somebody will start using this. But actually there is several use cases where this behavior is that doesn't cause any violation. One of them is backups. So read committed, read atomic doesn't provide the read screw, so we can do backups without implementing the Chladni-Lamport algorithm. So that's nice. Then it provides it's good for maintaining integrity of the secondary indexes, and also it's good for maintaining materialized view maintenance. So imagine that we have some website where we have a count of the messages, and we go to the list of the messages, and it doesn't match the actual count. So we want to avoid this situation. It's better to use transactions, but the transaction might be costly. But for read, but the read atomic, it can be fast, and it fixes this behavior. Let's see who implement this. So read atomic is implemented by the ramp algorithm, and it works this way. So again, we have a timestamp server. We have the data nodes, and on the data nodes we use multi-version concurrency control. So we store all of the previous version of the data. So how it works? We send to we ask the timestamp server for the current time, get the time, then we go and execute the prepare state, prepare phase, and the prepare phase, it doesn't log anything. It just inserts a new data to the database. So it inserts, but it doesn't mark them as a final. And also we send the list of the key who participates in who also participate in transactions. So in case of node A, the other key is B. In case of record B, the other key is A. So once we wrote this data, we send back to the client. Once the client got all of the confirmation, it executes the commit. During the commit, we just mark the the recently inserted values as current if the current timestamp is not greater than the timestamp that we inserted. So in this case, this timestamp is 1 is greater than 0, so we can go forward and proceed. So we updated both of the, we mark both new records as the current, and then we respond to the client, and after this stage, the transaction is committed. So we have covered the write transactions. Let's take a look how the read transactions works under the ramp. Let's make this example interesting and consider that the previous transaction has failed somewhere between along the way. So, and we want to read 2 records. What we do first, we just ask the system, please return me the current value. The current value in this case is A 50 and B 0. We can see that A was updated on the same moment as B. So B should have the version same as A, but the B's version is less. So we reconstruct the expected version of B, in this case it's 1, and ask the B not to provide the value of B at moment 1. So we ask the server to do this, and it returns new the required value, and after this return is done, we executed the transactional read. And the performance of ramp is really good. It's better than Granola, and unlike Granola, we don't wait for the other transactions to execute. So we just let them compete, and everything works way faster and has better latency. So, key takeaway. So the new protocols were invented since 2000s. Distributed transactions protocols finally became practical, and the cost overhead, depending on the workload and protocol, is less than twice compared to the baseline. So read papers, make experiments. That's fun. This is a list of the papers this talk is based on, and спасибо.
Now we have some time for questions. Any questions?
Thank you for the speech. In the last presentation slides, I saw the timestamp server. It seems to be a single point of error in the case. Am I right?
This timestamp server may be implemented in a replicated way, and in a replicated way, even if it's a replicated way, we can basically we can use something like sharded. So we run the server in the beginning. It reads the epoch time, increments this epoch, writes back to the storage, and then each server has an epoch time. Then on each time request, it have some additional field, and increment this additional field. We read from the majority of the servers, get the data, pick the maximum, send this maximum back. It's the servers update the epoch if it's necessary. Usually it's not necessary, and update the second field. And then we return this timestamp to the user. It requires 2 round trip, but we don't touch the disk during this execution, and it can be fault tolerant.
Okay. Thank
you. Maybe I didn't understand, but on this slide, like why the server B does not return the latest version by default? It's like number 1.
Okay, so this asterisk, I haven't explained what this asterisk means, but this asterisk means the current value. So when we execute the prepare phase, we just prepare some future current value, but we don't mark this as a final. And once we execute the commit, this record will be marked as a final. But there might be a failure during the execution of this protocol, so it might end up this in a corrupted state, or we might catch this state of in the moment of the modification, and everything is fine, but it's going to be fixed just in a second later.
Thanks.
Many thanks for a great talk. And could we go back to implementing of transaction for yes, for this way? Yes. Stop. And what we have to do if we have some issues on prepare state?
Retry.
Yes, retry. But how we? Yes. What? Now we have problem with prepare on B side, and after this we have a read request, and we will get value. We will not commit the phase A. Am I correct? So the situation when we read and have the different timestamps of two different nodes is impossible. Where okay, sorry. I think I found the answer for my question. So.
Great.
Any more questions?
I'm a good rubber duck.
So you measured everything, and am I correct to guess what it is published elsewhere? We could play with it and measure it ourselves.
It's not published yet, but I'm going to do this. I will refactor this presentation in some kinds of the post and attach all of the source code, and it will be published.
It will be very, very great, because so much protocols look into the same code, compare them between each other. It will be very educative.
Yeah,
experiment.
I'll definitely going to do this.
Okay, thank you.
Thank you, Denis. My question is about RAMP. Is this protocol already implemented in some kind of databases?
So I don't know. I heard a rumor that in Facebook there is a Apollo database, and it supports different protocols, and one of them is RAMP. But I heard it only once. I saw somewhere on the internet, and I've never heard about this again. So I don't know if it's true or not, and I'm not aware about the other database that uses it.
Okay, thank you. And if I can I ask you another question about Granola? What will happen if the transaction fails? So
at which moment?
For example, after first database got executed, so it should then notify the next database. So what will happen? It just will retry?
Yes, it will go to retry. Since this transaction is persisted in the database, when this node is bootstrapped, it reads all the unfinished transactions and tries to execute them in that order.
Okay, and what will happen if what happens if the second database fails, and we need somehow to initialize the full transaction from the base or not? So
we send these transactions in the full state to all of the nodes.
Okay.
Yeah. So if so they all can start acting as the first one.
I see.
Yeah.
Okay. Thank you.
The question is, if you interact with real banks that usually make more complex transactions that put some amount of money on reserve, then there is records that money reserved yet not sent to other, then records that about to be received, then back and forth. So could we actually avoid such complex protocols if we implement appropriate workflow instead of relying on database mechanism? What is trade-offs for that?
There is different approaches how to solve the task. One, as I understand you correctly, you're describing what Saga is about. Basically, we split the transaction execution by violating the visibility and execute them in different stages as a workflow and can eventually reach the consistent state. It's a one-off way of solving the task. Sometimes maybe it's hard to so as I understand this, this Saga approach is tightly bounded with the domains that you're implementing. Sometimes you can split them, as you said, as a step of the workflow. Sometimes you can't do this. So if you can, you can go with the Saga.
I understand this is more close to incremental structures. So you do not keep final result evaluation. You keep history of evaluation, then merge it. So you use final account, not the one digit, one amount, but that history of interaction with account. So you could just add records and keep results later. And finalize the records that is added to the database.
Yeah, it's a way to solve the tasks, but I can't answer why one is better. What are the trade-offs?
Just interested if it's possible to compare to such approach, how many interactions will be in some, if you use workflow or if you use two-phase transactions, and how many failures will be.
Yeah, if we get the workflow that we're interested in, we can implement this and see how it works. But it's good that you mentioned this Saga approach, because as we can see with Granola, we can do the transfer of money with overflow. We don't check the state of the account in the beginning. So if there is not enough money, we can go below zero with such stuff. But if you read not the paper Granola, but the dissertation that it's based on, it has a lot of interesting ideas how we can avoid this. For example, we can do the escrow accounts. So we first, on one node, create a temporary account and transfer the money from one account to another. And since it's happening on one node, we can check that there is a needed amount of money. And when it's done, then we continue execution with the independent transactions. And in this case, there is everything is working fine because we split this transaction into two stuff, just like with Sagas, and then we execute them. So it's basically like workflow.